engineers, data scientists, and machine learning engineers and researchers who are passionate about TensorFlow and related technologies. TensorFlow user groups are all over the world, and this is TensorFlow user group in Islamabad, Pakistan. My name is Ahmed, and I am working as a deep learning computer vision engineer at Grow.ai, which is a startup based in SS. Today we have with us Radi Cho. Uh, Radi is a 11th grade student from Bulgaria. He is a founder and ML researcher of ASBeauty.ml. And in this session, he will be talking and discussing about quantization techniques and quantization approaches for TensorFlow models. Thank you so much for taking up your time, and I'll pass it over to you.
Thank you. Thank you for having me. Hi, my full name is Radostin. I'm from Bulgaria, but people usually call me Radi for short. And as you introduced me, I'm working in the field of machine learning in the past few years, currently doing some research on quantization. And as my participation in the GD program involves giving some talks today, I will try to share more with you about quantization, how you can do quantization in TensorFlow and Keras, and also some new research-based ways to do quantization, which are more advanced. But if you're interested, I will provide the links so you can learn more about them. Just if you can confirm that my screen is showing up correctly, and I will start. Can you see?
Yeah, absolutely.
Yeah, thank you. Okay, so usually when I talk about quantization, I start with a visual example. In this case, you can take a look at this picture of a colorful llama. And I usually use the picture of a llama because later we will talk about language models. And probably some of you have already worked with Llama and Gemma, two models which are from Facebook and from Google. And so in this case, if we have this image and we want to reduce the amount of storage it takes, a question we can ask is how to do it, how to reduce its file size. And one way to do it is to compress the image. And a very simple way to compress an image is to quantize its colors. What does that mean? It means that you can take a few possible values, in this case, only 16 possible colors, and around all the other colors to those 16 possible colors. And as you can see, the image on the right, it's lower quality, but it's also taking very less space, because now I can save only the indices of the colors for each pixel and not the individual color itself. And this is quantization. This is how quantization works in concept. If I have to be more broad and more general, quantization is this process of mapping one set of possible values, which are very which is a very big set or a continuous set, to a small set of discrete values through some kind of rounding. And so in the case of machine learning models and large language models, quantization is used to reduce not only the file size of the language models, but also the amount of memory it takes to load them, to do inference with them, and also actually to train them. All of the people here, I guess, are interested in the revolution with large language models. And so probably all of you have noticed that in the past few years, all these language models that come from Google, OpenAI, Facebook, Meta, Microsoft, and stuff like that, they continue to grow in size and are very hard to actually work on consumer hardware, because consumer hardware doesn't have enough GPU RAM, GPU memory, and also actually even storage is now a bottleneck. If you want to download a very big model like GPT-3 or something like that, it will take hundreds of gigabytes to only download it. And then you have to have that much amount of memory on your GPU to actually load and use the model. And most of the models that we'll be mentioning today are open source, so you can actually apply quantization to them and see how it works in practice after the talk. So our idea for today is to see how this concept in the beginning, where I rounded the cores of a picture to some small set of possible cores, how can that be applied not to cores, but to the numbers, the parameters inside a big language model. So we'll be talking a little bit more about what are the recent ways of doing quantization more efficiently, because there are different ways to do it. I will be showing some code snippets from TensorFlow and Keras documentation, and also my own examples to showcase how that can be done in these frameworks. And then I will briefly also mention some things that I am personally working on in this field. Okay, so starting off, how do we store machine learning models, large language models, and deep neural networks in general? Like, they don't have to actually be language models. They could be some image classification models or image generation models. Usually the parameters of the models, the weights and biases of the neural networks, they're usually stored in full precision. That's 32-bit floating points. And sometimes we are also storing them in half precision. That's 16-bit floating points. So one parameter is usually taking 2 to 4 bytes of memory to be stored and also to be loaded into a GPU. And if you don't know the difference between the different floating point data types, the difference is usually in the number of exponent and mantissa numbers. So in 32-bit floating points, we have 8 bits dedicated to the exponent and 23 bits dedicated to the mantissa. So the mantissa is this numerical part, which we then multiply by 10 to the whatever exponent, or by 2 to the whatever exponent in binary. And of course, we have one sign for the bit, for 1 bit for the sign in each of these floating point data types. And so something that I wanted to mention in the beginning, because later on it could be useful, is that currently machine learning models are more and more safe in half precision. And not only FP16, but also BrainFold 16. BrainFold 16 is a kind of new data type introduced in, I think, NVIDIA GPUs. They support it. And the idea is that it's again taking 16 bits of space, like the normal FP16, the normal half. But this time, the number of exponent bits is actually matching the bigger precision data type. And the idea here is that the range of the BrainFold 16 data type will be the same as the range of the floating point 32. Now, the individual steps, like the precision of the individual numbers that you can store, of course, is very, very low in the BrainFold 16 compared to the floating point 32. But the idea now is, because the range is the same, you can store the same minimum and the same maximum number as the full precision models. And so some GPUs have kernels that support even multiplications or mathematical operations between numbers saved in the 2 distinct data types. Only the first one is much more quicker to work with, and that's why it's now preferred to be used for many of the large language models. So if you go to Hugging Face, let's say, or Kaggle models, and you download some models, you might notice that many of them are actually in BrainFold 16 and not the other 2 data types. Some of them you can convert if they are not. I wanted to briefly mention that in the beginning. So in TensorFlow, if you want to take a model that's full precision and then convert it to, let's say, half or FP16, you can do that using the TensorFlow wide converter. The idea here is that they put these quantization abilities in TensorFlow in the TF-wide library, because usually quantization is used when you have limited resources, and the TensorFlow wide library is especially designed to create models and then use models on edge devices, on smartphones, on microcontrollers and stuff like that. So you can find in the TensorFlow wide library many of the methods that we'll be talking about today. And here I've shown a simple example of how you can take a model. This is a very simple convolutional neural net implemented with the Keras sequential API. Perhaps many of you have already worked with such kinds of simple neural networks. And when I define such a simple CNN, then I can use the TF-wide converter. In this case, I can just pass it from Keras model and pass my model. And it actually doesn't quite matter if I define it with the sequential API or some other way, because in Keras you can define your own models which are not sequential. And when I initialize the converter from the model, then I can specify what kind of optimization I want. As far as I remember, there were different types of optimizations. For example, when quantizing, optimize for latency or optimize for speed or optimize for storage. I'm not sure what the full list of options was, but as far as I know, currently they are deprecated. So you should actually only use the default optimization. So it will just cast the numbers to the lower precision data type as it's defined in the TF-wide converter. And then you specify actually what's the data type you want to cast your model to, and then convert it with converter.convert. And now your model is taking 16 bits per parameter instead of 32 bits per parameter, which is actually you've reduced its size by half. That's great. And then when you want to use such models, which are in lower precision, you can use the TensorFlow wide interpreter. The idea is that you're better off using some predefined logic that's inside of the interpreter to use the model in the lower precision data type. And you do not want to cast it back to full precision to use it every time, because that will be very inefficient, very costly. And it will defy the purpose of doing quantization in this way or casting in this way to lower precision data types. The idea of the TensorFlow interpreter is that you can specify a model, which we previously, in the previous slide, I showed you how we can create. And once you provide it with such a model, you can allocate some memory. And then you can also provide a dummy input to the TensorFlow interpreter, so it knows what shape of the data will be passing through the neural network, what shape will be the input, and so what shape will be the inner dimension, the latent the dimensions, and what will be the patch size, and so on. So in this case, with my simple convolutional neural net, I'm passing a simple image, which is an empty image, but it's having some size. And then I can set this dummy input as an input, and then invoke the TensorFlow interpreter. So it will cast my inputs to the lower precision data type, pass them through the model, do the multiplications and additions by the weights and biases inside of the interpreter with the lower precision data type with floating point 16, and then it will return the output with this get tensor. So you can insert tensors inside of the interpreter, and then once you pass them through the network, it will this output will be allocated to some tensor, which you can then get it out of the interpreter to use it in your own code with .get tensor and pass it the index of the output that you previously defined, that tensor will be your own output. It's fine if you find this a little bit confusing at first. Me myself also finds it a little bit confusing. The idea is that now I'm trying to briefly let you know of what's possible. And afterwards, having this information in mind, you can probably go by your own and check out the documentation, check out some examples and exercises, and actually learn how it works in practice. But the idea is to see that here it's possible with the TensorFlow interpreter, the TensorFlow wide interpreter, to run this model in lower precision in FP16 with data, which is casted to FP16, and get the output out of the calculations, which are done with the lower precision model. That's great. So we reduced our model size in half, used our model, got some outputs, and that's great. But that's not enough, actually. As I talked in the beginning, many of them currently used large language models are very, very big. So even if you reduce them by half, it's not that big of a difference. Or yeah, it's a very big of a difference, but it's not enough big of a difference. And so from here on, there are some techniques which you can use or apply, or at least theoretically try to achieve to go below half precision. So you can go to 8 bits per parameter or 4 bits per parameter even, and some crazy research is going on currently to try to reduce the number of bits per parameter for kind of lossless quantization down to 3 or 2. Um, but how does that work? So if you try to construct lower bit data types, for example, if you want to have a data type which is in only 8 bits, or even lower than that, and you cast the model parameters to that data type, it will be too lossy, it will be too noisy. That's because in below 8 bits per in below 8 bits, you cannot construct a sensible data type which has enough of possible values. So it will be very rough. And just casting in this simple way in which I demonstrated with the two small code snippets, just casting in that way won't be enough to save the model and make it work afterwards. So there are some smarter ways to do quantization in less than 16 bits per parameter, in 8 bits per parameter, or less than that. So I will briefly mention those. For example, the most standard or the most popular way of doing simple quantization in 8 bits is the so-called scaling quantization or absolute maximum quantization or int8 quantization. You can find it with different names. Usually the idea is that you can take the numbers from your model. Let's say we have a few parameters in our model, and they vary from a very small number to a very big number. So we usually take that range and scale it back just to the range of integers that we can save in, let's say, 8 bits. In 8 bits, we can have 256 in total number of integers. So we can divide by the maximum number in the original range. We can divide by it, and now all the numbers that we have in the model will go from minus 128 to 128, let's say. And then we can round them. Like after the division, there will be some floating points, but we can round them to the closest possible integer. And now each each rounded integer will take only 8 bits because we're working with 8-bit integers. And we save the scalar that we divided by, like we can save the absolute maximum number in full precision. And then if we want to reconstruct an approximation of the original numbers, we can rescale by that absolute maximum number or by that scale. Like we can multiply back the rounded integers by the full precision scale, and we will get numbers in the original range, which are very close to the original numbers. Like they're not the same because we went through this process of rounding to integers, but now after the multiplication, we will be again in the same range, and also we will be having numbers close to the original. Now, as you can see here, this type of quantization requires saving one extra parameter. So instead every number being saved in only 8 bits, like it's saved in only 8 bits, but then you save one additional number, which is, let's say, 32 bits, because it's in full precision, and that's this scale as here. So in total, your effective bits per parameter will be 8 point something, 8 point something very small, depending of what's the group size. how many numbers you're quantizing at once. And later in this talk, I will mention that it's a very dumb idea to quantize all the numbers in a model at once. Usually people quantize smaller groups of numbers. And I will mention that in a minute. But if you can notice a problem here, it's probably that when you scale between the original range and the quantized range in this kind of quantization, you usually are prone to uh, having an asymmetric quantization, which is wasting some quantization bins. What I mean is that if you take a look at the first picture, we have some numbers to the right of the zero, which are further to the right than all the numbers which are to the left of the zero. And so when I do my scaling to the left here in my quantized range, I won't have any numbers that are quantized to the smallest number, let's say. And so I'm wasting numbers. Like I have a few values here, which I could have used, but I'm not using because my scaling is asymmetric. And to overcome this, I can introduce one extra parameter, which we usually call a 0 point. And the 0 point can be as simple as just take the smallest number, subtract it from all the other numbers. And now your numbers will go from 0 to some number, then rescale them, and your quantized range will look something like this. And then when you scale them back by the scale, you also add the 0 point. So you're again shifting the numbers to the left of the 0 when you add the smallest number. And in this way, you now don't have this asymmetric problem, because before you did the shifting to the left or to the right, you only had numbers in a range that is from your smallest quantization bin to your biggest quantization bin. So you fully utilize the smaller precision data type. As you can probably guess, this takes a little bit more storage. So you are saving not only a scale, but a 0 point in full precision as well. But that's usually negligible because you're quantizing many numbers together, and you're saving only one scale and only one 0 point for that group of numbers. And so going to some TensorFlow code again. If you want to do something like int8 quantization in TensorFlow and use it also with Keras models, you can again use the TensorFlow wide converter, and you can use actually the ef.int8 or uint8 data types to convert your model to, and that will do a way of int8 quantization. Now, something very important that I have to mention here is because of the simplicity of this way of quantization, like it's linear. Like you can scale the numbers to the quantized range and then do some arithmetic, like add two numbers together in quantized range. And if you then dequantize the output, dequantize the result, it will be the same as first dequantizing both of the numbers and then adding them up or multiplying them up. And that's very interesting because usually working with smaller precision data types like int8 is taking less resources on a GPU or whatever device you are using. And so in TensorFlow, you can actually make the model work in int8 and the data to be casted to int8 and do the arithmetic in lower precision data types, so you utilize your hardware better, instead of first dequantizing and then using the model. And to do that, you usually set the inference input and output types of the TensorFlow converter when you're using a model. And then you, again, convert the model to this data type. Now, when you're working with such a small number of bits per parameter, usually the converter needs some data. So again, it can optimize like the quantization for the shape of the data and the proper distribution of the data. So you can pass it some representative data in this way. So it knows what data your model will be using when inference is done, so it can better optimize the quantization process. I won't be getting into details here what that means and what that's doing. But again, as I said, for the specifics of these processes, you can go to the um, documentation later or ask me questions and we'll try to clarify this. But I want to mention that it's possible to use int8 quantization in this way in TensorFlow. Great. And then you can also use tf.quantization. This is another part of the TensorFlow library in which you can do more customized quantization. For example, you can pass it the minimum and maximum range. So those are these numbers, but you can pass them manually. And you can also pass manually how the rounding is done. Do you round to the bigger or to the lower or to the closest integer and stuff like that. So you can manually customize this way of quantization. And why would you actually do that? Like if quantization is usually done in this simple case, why would you want to manually change this number? Well, that's because you don't have to do quantization in the standard int8 way. There are more advanced ways of doing quantization, and I will now try to go through them. We won't be taking a look at their implementation because they're um, kind of not our job. Like we usually use them from some libraries that provide them, but there are also research papers with those quantization techniques, which you can read if you are interested in, and you can try to re-implement on your own for some reason if you want to. So first of all, in this case, I wanted to showcase OmniQuant. OmniQuant is a very recent paper that introduced a new quantization technique in which actually the maximum and the minimum numbers in int quantization, like OmniQuant is an extension of integer quantization, which I already explained. So in OmniQuant, the maximum and the minimum values of the original range are first scaled, moved a little bit to the left or to the right before quantization is performed. And the usual idea is that, for example, if you move it a little bit to the right, the leftmost number, you probably will quantize worse one of the numbers, but you might quantize better all of the rest of the numbers. For example, I'll go back again to my picture. Here, if my maximum, let's say I'll be moving my maximum value because the picture is better suited for that example. So if I manually move this maximum value to the left, I will quantize worse this number. So this number will be represented poorly. But because I narrowed my range, the precision of how I quantize those numbers, they'll be quantized better. And that's why OmniQuant works. Because at the cost of quantizing some numbers poorly, it's quantizing other numbers better. And through finding optimal scaling factors for the biggest and the smallest numbers in the range, you can actually produce a model which is quantized in the same number of bits. So OmniQuant is again saving a scale and a 0 point. They are taking the absolutely an equal amount of storage and RAM to use, but the final model is working better because we found such scalars that they are quantizing some of the numbers, some of the more important numbers better. Now, in this research paper, they describe how you actually find these gammas and betas. That's the interesting part of OmniQuant. You find them by using gradient descent, passing some data through the model, and seeing which gammas and betas are working better for quantization. I won't be going through that here, but after the talk, I will share these slides with the links so you can go by yourself and see how you can find such scaling factors by which you can scale and get a better model. And once you have found them, you can substitute them here and use them with the TensorFlow library to implement some way of doing OmniQuant on your own, let's say. Then there's blockwise quantization. Blockwise quantization, it's actually not a thing on its own. It's usually used with the techniques that I already explained, or with the techniques that I will explain afterwards. So I already mentioned that it's a dumb idea to quantize all of the numbers together um, if you're doing int quantization or omni-quant quantization. Because the int quantization and omni-quant quantization, they're relying on the range of numbers, like the biggest, the smallest, and the distribution in between. If you just quantize all of your model at once, the biggest number will be very, very big outlier, and the smallest number will be very, very small outlier, and quantization will be very, very poor. But that's why you can divide the tensors or the matrices of your model into smaller blocks or groups. Different papers and different resources call them different ways. I usually call them blocks, and that's why it's called blockwise quantization. So basically, if you have a weight matrix, you can just take the first, let's say, 128 numbers, quantize those, then take the next, quantize those, take the next, quantize those, and so forth. And as you can probably guess, for each group of 128 numbers, you were saving 1 0.1 one scale. But that's, again, ineffective bits per parameter, not very significant, because you have only one full precision number for quantizing 128 numbers. And you can actually play with blockwise quantization. You can try different block sizes and reduce the memory even more. But usually, it's standard currently in all of the research papers and all of the libraries that people use for optimization to use 128 numbers at a time and quantize them. Then there's quantile quantization. Quantile quantization was introduced in a paper which was called QLoRa. Probably some of you have already discussed that paper. It's a quite popular one. And the QLoRa paper, it has two important parts to it. The first one is they quantize a model, and then they fine-tune the model with low-rank adaptation to overcome some of the performance loss from the quantization. For our purposes, we won't be discussing the second part of QLoRa, but the first part of QLoRa works by relying on the distribution of the weights. The weights in a machine learning model turn out to be normally distributed. So you have a lot of weights which are close to zero. And you have less weights which are much, much smaller or much, much bigger than zero. They roughly follow a normal distribution. And because that's the case, QLoRa says that we can take some quantiles. Quantiles are these parts of the normal distribution which have equal probability density below them, and use those numbers as rounding points. So instead of rounding to the closest integer, you can round to the closest quantile. And this will again take the same number of storage or memory, because you're again saving the index of the quantile. You're saving not the value of the quantile, but the index. Like you in memory, you save, okay, this number is rounded to the first or to the second or to the third or to the fourth and so forth quantiles. And when you need the numbers, you can do a quick lookup table, which has like a 16 possible value hash map or table or whatever, and just look up those index maps to this floating point number. And in this way, you can do the quantization. And it turns out as you can read in the Quora paper, that doing this way of non-uniform quantization actually works better. And that's something that I actually worked on in the summer. I was doing a research project in which I was trying different ways of non-uniform quantization, um, which work better than the standard integer quantization and also some other ways of uniform quantization. This distributional quantization is my thingy. This is something that I worked on previously, as I mentioned during the summer. The idea was that Q-Aura relies on a specific normal distribution. The numbers in Q-Aura are distributed normally, and they use only a single lookup table that they pre-computed before quantization. And my work was actually together with Professor Yoon Kim from MIT, which I want to thank him, to acknowledge him. We wanted to see what if the optimal distribution from which we take the quantiles is different from the one that's used in QLoRa. So it could be, again, a Gaussian distribution, but with a longer tail, or a smaller standard deviation, or it could also be some other kind of mathematical distribution. And we can take some quantiles from it and use those as surrounding bins. So we tried that, and we came up with this distributional quantization way of training. I, again, won't be going through the details, but I will later send you a link to a paper that we wrote, which explains how this works. And when we tried this in combination with blockwise quantization, so we take a block of numbers, then quantize them by finding the optimal standard deviation or the optimal distribution in general, and replace the indices with the quantization bins. So we do dequantization, we test the model, and these are the results that we got in that experiment. By warning the standard deviation, it turns out here, this is in the blue, you can, in the same amount of storage that NF4 uses. NF4 is the normal fault for data type that's introduced in the Quora paper, and also int8, int4 quantization is also taking this amount of space in the green line. We are producing much lower perplexity and much lower reconstruction error of our results. So yeah, I won't be going into the details here, but the idea is if you warn the distribution and its parameters by which you can quantize, you get model with much less error, having absolutely the same amount of storage used. And then going back to some TensorFlow code and techniques, when we are doing this research, tests and experiments, we are usually doing it with fake quantization. And so you might be thinking, what's fake quantization now? The whole idea of quantization was to save storage and resources, right? And to actually utilize our hardware better. And in fake quantization, you do some kind of quantization, but the inputs, the outputs, the numbers themselves, they are still stored in floating point 32 or in full precision. The thing that's specific to fake quantization is that you restrict the number of possible values that you will be rounding to. Let's say if we are doing 4-bit quantization, so 4 bits per parameter, each parameter will be only one of 16 possible values. And we can do our way of quantization, still store everything in floating point 32, but then we can run the model on our current GPU because we don't yet have implemented a data type, which is, let's say, 4 bits. So we can quickly test if the model works, if it converges, if the inference is good, if perplexity is good. And once we've found that our quantization is good, then we can go to the rabbit hole of implementing ourselves a new GPU kernel, a new library, and stuff like that to actually use the 4-bit quantization that we implemented. Because to do anything lower than 8-bit quantization, you have to do very complex things like defining your own data types and stuff like that. Because below 8 bits, there are no very useful data types to save your numbers to save storage. That's why you can find in some of these examples that I am showing to you that they usually use fake quantization first while they're optimizing their parameters. And once you have like the optimal standard deviation in our case, or the optimal betas and gammas in OmniQuant, then you can go to the rabbit hole and implement the actual quantization with the TensorFlow wide converter or with your own GPU kernel and use the warrant parameters. And as I mentioned, quantizers can be defined on your own with custom codes. They are usually callables, so you can create classes which extend the TensorFlow quantizer's quantizer. And then you can create this callable in which you can actually implement your own quantizer, which is doing something more complex. In this very simple case, my quantizer is just clipping the numbers between 0 and 6. But that's a very dumb quantizer. It won't do anything useful. But the idea is that it's fully custom. Like you can do whatever you want in this quantizer and implement all of these more advanced ways that I already described. And then all of this was mostly about post-training quantization. So you have one model, which we cast to half precision, FP16, or we quantize with integer 8 quantization in 8 bits per parameter, or we apply more advanced quantization like OmniQuant or distributional quantization to do it in 4 bits per parameter. That's once we already have a model and we want to quantize it to less bits. But you can quantize a model or implement the quantization procedure even before the model is trained or fine-tuned. And the idea is that while training and fine-tuning the model, if you're applying the quantization on that stage, then the optimization process will compensate for the uh, loss of the quantization. And here, I don't have much more slides on that, but I want to just quickly show you this resource from TensorFlow documentation, where they're talking about quantization-aware training. So once you have a model, here's a very simple example, like the example that I showed you earlier today. Instead of quantizing it once it's trained, here they first train it, but then they will show you that instead of quantizing it after it's trained, you can first implement some quantization approach. Let's say you can use this quantized model method from Keras to quantize a model, then compile the quantized model so it's quantization aware. And so now this quantization-aware model, when it's invoked and data is passed through it, its parameters will be around and stuff like that. And then the whole optimization process will have this step of rounding and of losing useful information, which will actually help the model to learn weights which are better suited for quantization. And then you can train your own model, like train the quantization-aware model like you usually would with TensorFlow. And this usually results in a much more performant models once they're quantized. Of course, this requires training the model again, which is costly. Some people do calibration fine-tuning or just some kind of small fine-tuning of the model with quantization-aware training to just optimize the quantization to be not as rough as only post-training quantization. So the idea is that you don't have to train the model from the beginning with quantization-aware training. Some of the techniques take an already trained model, quantize it, and from there on, they fine-tune it with quantization-aware training. Of course, some small number of epochs or some small number of iterations, and not very big data set of for calibration. And again, in this way, they optimize the quantization procedure and its parameters to be more prone to the loss from the rounding that's done in the quantization. And so, yeah, I think that's most of what I wanted to show you today. A quick recap that I want to make is that I wanted to show you what's possible, and a lot of things are possible in TensorFlow and Keras for doing quantization. You can use lower precision data types, not only the bigger, the full precision floating point 32. You can cast your trained model to half precision. You can use it in half precision with the TensorFlow interpreter and the TensorFlow wide converter. Then you can use int8 quantization with TensorFlow, and then you can also modify it to accommodate for more specific use cases or for more complex use cases like OmniQuant. And then finally, you can implement your own quantizers, which might follow, let's say, my own distributional quantization or some other way of quantization. And once you do this, you can do fake quantization to test if they work without the need of writing new kernels. And once you've done that, you can write a new kernel, which I won't be going to work with whatever data type you decided. For example, OmniQuant also works with 3 bits. And finally, you can also do quantization-aware training, or at least fine-tuning to better suit your model to the quantization process. That's in general what I wanted to share today. Now, if you have some questions, please go forward, and then I can also share more details in any specific direction if you request me to. Do we have some questions? Someone said, can you explain it again, sir? But I didn't see that. So can you mention which part of the slides you want me to explain again? In the meantime, I will share these slides. I think they have some useful links for you to go through if you want. Here are all the and also this one. Yeah, why and when we need quantization. So let's say you want to use Gemma or Llama 3. These are language models that you can run on your own device if you have the resources to. And so, but let's say you only have 20 gigabytes of VRAM. So here in my own apartment, I have a GPU which has 24 gigabytes of VRAM. So The Llama 3 8 billion model, it has 8 billion parameters. And each parameter is taking 4 bits if it is 4 bytes if it is loaded in full precision. So it's roughly taking 32 gigabytes of RAM if I want to load it and then use it. And then I won't be able to fit it into my own GPU because I have less than that. But if I do cast it to half precision, it will only take 2 bytes per parameter. So now I can actually load it in only 16 gigabytes. And I can fit that in my own GPU and use it. And then we can go further, like in 8-bit quantization, each number is taking only 1 byte. So I can load it in 8 gigabytes, roughly. And I can load actually now multiple instances of my model on my device. Of course, that will be lossy, so the model won't be as good as the original one. But as far as it is good enough to be used, that's great. Now I can use the model on my own GPU, and I previously couldn't do that. Did that one help you to understand it better? Yeah. Okay. So yeah. I advise you to check out the resources afterwards because it will be very helpful to you to actually know some of these things. Because when we are working with big models, we usually cannot load them on our own devices, but through quantization we now can. Yeah. Do we have some other questions?
I don't think we have any other question. Our uh, call time is also about to end. So I would like to thank you for taking our time for this session and thank everyone joining us. And I would like everyone to please fill the feedback form so that we can roll out certificates as well.
Thank you also for having me. It was a pleasure to try to share some of the quantization things that I work on with you.
Thank you, everyone. Take care. Bye.
Thank you.